Starting here real fast as soon as all my bits and pieces are in the spots I want them. And I think that is now. Hot dog. Cool. Okay. So this is exam review 2 for Physics 201 at Texas A&M University. And so I will do it exactly as I did last time, talking to somebody or maybe nobody. I know that I saw some people there in Twitch. We'll find out if any of my students join me in Zoom or not. All right, so, oh, look at that. Oh, I know what's going on here. I would like to select page 7. There we go. Now I can write in things. Okay. Let's see here. Come here. Grab it. There we go. Cool. All right. So starting out with the lovely equations that we have from, well, I did talk about friction last time. I'll talk about friction again. Friction in springs, because those may or may not be on this exam. I heard no restrictions given, so I shall go ahead and talk about friction here. Because it wasn't on, friction and springs weren't on exam 1. They may be on exam 2. I don't know. I've heard precisely nothing. Okay, so friction, we have, if you have an object sitting somewhere, we can apply force to it. Some force gets applied to this, and simply because it is on a normal real surface of some kind or another, there will be a force of friction opposing it. Force of friction, if V is equal to 0, meaning it is moving nowhere, then force of friction must be provided by static friction, and they must be equal to equal to the force that has been applied. Force of friction must be. Hey, look at that! There is somebody in my chat. Come again? Hello? I heard somebody in my Zoom. Somebody logged into my Zoom. Anyhow, so the static friction must be equal to the force that has been applied in order to make sure that this object does not move from where it is located. If V is not equal to 0, then the friction is no longer static. It is now a force. Friction is now a kinetic friction, and it will be less than any forces that, well, it doesn't even need to be less than or equal to any forces that are applied to it, because it is in motion. But it must be equal to, it is definitely equal to, Tyler Whitehead, Zoom. That sounded important. Email says something important, may have said something important. Exam 2 review from Mr. Box. Thanks for doing this last video. It was a huge help. Yes, you're welcome. I assume you'll be back. And Ty Whitehead has given his thesis defense by Zoom. Okay. All right. Friction. So if it's moving, then we have kinetic friction that is equal to mu k times the force that is normal to the surface. So since we're sitting on a surface, there must be a force normal to that surface there. If we have a static friction, then static friction must be less than or equal to mu static force normal. If the force becomes greater than this friction here, if the applied force becomes greater than the static friction will allow, then the static friction will break. And then we're back into the kinetic friction. And I find that in most cases, in most problems involving static friction, it's a conditional force. That is, it is the force necessary to make sure that the net force is equal to 0. is similar to normal force, which is the force necessary to make sure that the object does not fall through the surface. That, or alternatively, to make the forces in perpendicular direction equal to 0. I think that is about it for friction itself. Are there any questions from anybody who happens to be in my Zoom? Miss Flores is in there. Good morning, Miss Flores. All right. Now on to the stuff that is definitely supposed to be on exam 2. We have circular motion and orbits. If we have an object going around in a circle, like so, it must have a velocity of some sort or another, v, going around the circle. The circle obviously has a radius, r, and in order for this object to keep going in the circle, there must be a centripetal force pulling inwards, and I think I'll just call it Fc, pulling inwards. It must be provided by something. In the case of gravity, in the case of orbits, that something is gravity. There are a non-zero number of problems involving buckets going around in circles on a string, in which case that tension, another conditional force, is providing that the force necessary for that centripetal force. If you are in a car going around a turn, depending on how that turn is constructed, there may be some force. Some of the centripetal force may be provided by the normal force of the surface, if the surface is banked. If it's a flat surface and you're taking a corner like at a intersection, that's provided by friction. And then if you're in a plane and you're taking a corner and that's banked, that centripetal force is provided by the lift force. I think that's most of the interesting problems you're going to come across in this particular class, where you have centripetal force involved. Most of the time we are looking at a uniform velocity, in which case the velocity is the circumference divided by the time to do it. So that's a capital T being a period of the going around in circles here. And of course the circumference is 2 pi r, so here's our velocity. Woohoo. This is force of gravity. We have mass 1 and mass 2, and then Newton's constant provided here, divided by r squared, where r is the distance from the center of the planet you're going around to the orbit in question. There are some trickish questions that exist out there where the problem will say the orbit is so many kilometers above the space shuttle or the satellite has an altitude of so much, in which case you have to then also add in the radius of the planet in question. I think that's pretty much as trickish as that gets. And then of course when we have period here, this is period of orbit. And I think that is about it for centripetal for going around in circles. So real quick, an example that's not an orbit. You could have a bucket going around in a circle on a string or an arm, in which case we have tension coming down. And so in this particular case we have this here, we want force centripetal equal to mv square on r. So this is basically a net force here. And if we're at the top, then we have F gravity plus tension. And tension will provide any other force necessary to make this net force, this centripetal force, come out correct. And of course, if we're at the bottom instead of at the top, come here, pulling up instead of down, then we have the mv squared over r equal to tension pulling up minus gravity pulling down. And then so in this case, our tension is greater at the bottom than it would be at the top. Do I have any questions about centripetal force from anywhere yet? Hearing none. Let me clear out some space. Okay. We talked about work and energy and all this lovely stuff here. There is. Wait a minute. Did I miss springs? I did miss springs. Let's talk about springs for just half a moment here. So we have springs force here. Spring force is not usually talked about on exam, not because we don't like it, but because we find it's potentially much more entertaining. But if we have a spring and some object here, and we can then stretch it out from its origin, and this distance here becomes our x, and it wants to pull back this way. The fact that it's pulling back, so this displacement here, this is less than 0, and this is a force in positive direction. So our force spring is minus kx. Minus will return us back to the origin. And x says that the further we get away, the more the spring wants to pull on it. But I don't think we like these bit of force questions too much. Like I said, we find the energy questions to be much more entertaining because we as physicists, we like our conserved quantities, and energy is a conserved quantity. Force is not conserved quantity, and so we don't like talking about forces any more than we absolutely need to. Control Y, put that back, there we go. So now we get to energy. Come here, energy. Energy is a conserved quantity, or it may be a conserved quantity. Sometimes we have inelastic things where energy gets absorbed, or usually it gets absorbed into something. So like friction. So we have work. All this, there's a lot of stuff in here that. So we have that work here. Work is equal to change in kinetic energy. But that is also equal to force vector dot our displacement vector. In our particular case, we do not like involving arbitrary forces and arbitrary displacements. So, because that calls for calculus, and this is not a calculus-based course, so we end up with Fs cosine theta. So if we make a motion from here to there while applying a force, let's try again. If we make a displacement from A to B while applying a force in this direction for some strange reason, which would imply that there's probably also a force off in this direction, then we end up with, so then this going from A to B, this force here does this amount of work. So what actually turns out to be more often the case is that work is equal to our change in kinetic energy is equal to the sum of forces times dot product times the displacement cosine theta theta I. And there's only one S because it's the same object that's making the motion. But there may be more than one force that's being applied to the object in question. And so you may have to do a sum of forces. A sum of work done by individual forces. I don't think you'll see more than one. As this is a multiple choice exam, you're probably only going to be looking at, it's most likely that the total work will also be equal to the work done by a single force. That may not necessarily be the case because some people get a little crazy with even their multiple choice questions. But for a multiple choice exam to be a good exam, each multiple choice question should only involve a few steps so that a test of knowledge can be actually done. But people can be crazy, and those people are deserving of all the hate and pain in the grading of that exam. I have been there. It's not fun. I've done it to myself. It's not good. So that's individual work there, and that's also equal to, if the work in question is done by a conservative force, that would be equal to a minus, right? It should be minus. Yeah, it should be a minus delta change in potential, or as I prefer to write it, minus change in potential energy, like so. And we've been provided several different energies here. So we have several different potential energies. We have U elastic, which is 1/2 kx squared. This is for springs and other such, for any kind of spring or elastic item, so rubber bands and elastic bands and things like that. We have U of gravity. This is mgy. This is for short range. Like dropping it over a meter or over the distance of your house and stuff like that. There is for long range stuff, which is not part of this class as far as I remember. You could also come across this version as well. This is long range. Oops. And not part of this exam. But it's a thing that exists, but we won't deal with that. That will not be part of this exam. Just the short range. That's all you have to do. Oops. That's all I have to deal with. There's the short range one. Kinetic energy. Kinetic energy is 1/2 mv squared every time. Nothing changes there. And then we have this lovely equation here. Basically, so there's a thing called work energy theorem. I don't know why they have to say use the work energy theorem. It's like no, it's just energy conservation. They like to partition things up by the book. Other people, when they do their energy conservation, get rid of. All right, that's probably one to me. When the book does it, they usually do their energy conservation as energy final is equal to energy initial plus their work other, which they will provide if there's some other work like that. Yeah. Oh, right. This is basically how I ended up dividing it. You could also do it as delta K E equal minus delta, delta U, and then plus work other here, right? Make sure things signs on. Yep, work other. Could be done this way. I like doing it this way. Like the book has it where it says where did the energy come from, where did the energy go, which means that more often than not, my work I end up with my friction. My work of friction quite often ends up on the final side because I like to know that the energy went into the work done by that friction rather than over here where the work with the work other where it's like other work went that's not conserved. It's like, oh, come on, really? But each style to his own. We may come across a problem like that or not. Then we have power. Power is equal to the work done over the time to do it, and is also equal to force vector dot v vector, which is the same thing as force v cosine theta. Basically, same idea as the as the work done over here. Except it's done over time because let's see here, to do v in this particular case would be an s over t, or displacement divided by the time to move that distance. And then we have momentum. Momentum. So momentum is equal to m times our velocity. A change in momentum is an impulse. This is impulse here. And then right. And so if you rearrange this, you end up with change in momentum vector over change in time is equal to force vector. And if you want to, you could do some calculus on this, and then you could figure out how to make rockets work with the reaction forces. The rest of this here is basically all about center of mass, position, and velocity, and saying that if you have a center, whatever you end up doing to the center of mass, it applies to the whole system kind of thing. So this is a total momentum of the whole system, and this is a mass averaged position of the object or the whole system, and hopefully we'll come across one of those. And it blows people's minds when I make use of it for some strange reason. This here. We'll see if we can make use of it yet. Any questions yet? Do the exam itself. No chat room, no chat there. Okay. Is Ms. Flores still with us? Yep, she's still there. Okay. Alright, small rock is thrown straight up from the surface of a planet with an initial speed of 8 meters per second and returns to the surface 4 seconds after being thrown. Air resistance can be neglected. Planet is this big. What is this radius? Okay. Right. Gravity question. Goes up with the speed, comes back after a certain amount of time. That would imply a velocity? Yes. That would imply an acceleration. So we bust out some kinematics. Oh, no, we'll come back to that. This here. So we have, help to draw on page 1. So we have, here we go. This here, where was I? Right, v squared is equal to v, all right. Oh, that's not gonna do it, is it? Nope. That's not gonna be helpful. Nope. Next one. V is equal to v naught plus at. That'll work. There we go. V minus v naught divided by t is equal to a. So we have that we go up 8 meters per second. So we are coming down minus 8 meters per second on the other side. Minus 8 meters per second over here. Divided by the 4 seconds to do it. So that's minus 16 divided by 4 is 4 meters per second squared. We were told the mass of this planet. So we have force of gravity is equal to G m1 m2 divided by r square is equal to this here that would be a mg m1's go away, and we find that g, which is what this is, 4 meters per second squared. We're looking for the radius. So then, g comes down, and we take the we trade those and take the square root. So we take the square root of g m2. That's called g. Little g is equal to our r. Right? Yes. All right. Square root. Okay. Come on. This here, 6.67 times 10 to the minus 11. Six 0.67 times 10 to the minus 11, there you go, times the mass of this thing, 5 times 10 to the 24, divided by 4, and that is equal to square root 6.67 e minus 11 times, that's a lovely number, there you go, 5 e 20, that's missed, 24, divide 4, and execute. Alright, that's a big number. 1, 2, 3, 4, 5, 6. 9.13 times 10 to the 6 kilograms. Oops, nope, that's not kilogram. Meters. We're looking for a radius. It's got to be in meters. 9.13. Ah, look at that. Very good. Any satellite orbits the Earth in a circular orbit that has a certain radius. Okay, not a trick question. Radius, not altitude. Very good. What is the orbital speed of the satellite? Note the mass of the Earth is this much, and the radius of the Earth is that much, which is not relevant to the question. Well, it may be relevant. What is orbital speed? Nope, that is not relevant. The radius of the Earth is not relevant to this question at all. Alright, so we need, let's see here, we have a period. We have a question for period, I believe. We're told a radius. Radius, mass, gravity. Yep, there it is. We'll take that one. So T is equal to 2 pi r to the 3/2 divided by the square root of mg. That is the question. That is the equation. 2 pi r cubed to do r and gm. Yeah. Yeah. Good. So now we have a period for this thing. Plug our numbers in that. 2 pi, we have a radius of the orbit, which is 8 times 10 to the 7 meters, whatever. Try that 7 again though. 7 to the 3/2. I like my units, but sometimes I don't have the space for them. Make sure you don't do something stupid, like what I tried to do here. Mass, right? Yep, mass, that's 5.97 times 10 to the 24 kilograms, whatever. 6.67 times 10 to the minus 11. I'll get whatever units necessary there. And now we can ask the question, what is the period of this thing? So we have 2 pi 8e7 to the 1.5 divided by the square root 5.97 e24 times 6.67 e minus 11 and execute. In seconds? Yes, they want it in seconds, okay. That is 225,000 seconds. 225 kiloseconds. More or less. Now we need velocity. That is 2 pi r divided by time. So punch in the 2 pi 8e7 divided by AINS. And that comes out to be 2,231 meters per second. Ah, there we are. Very good. 2230 meters per second. That is exactly what I'm for. Very good. If there are any questions, feel free to shout them or drop them in the chat, whether you are on Twitch or in my Zoom. Alright. A small block, mass of 1/5 of a kilo, is released from rest at point A at the top of a frictionless track. Vertical distance of h. So we start here, 0 velocity, drop that far, some h above the ground. At the bottom of the track there is a circular loop, radius of 2 meters. 2 meters loop. Why did we solve for the period if it's asking for orbital speed? Because I had an equation that related the full radius, the full circumference of the orbit, and so I needed the period of that orbit to find its velocity. If I wanted to, I could have taken this equation here and dropped it into there, like this here. This 2 pi we cancel with that 2 pi. We get square root of mg on top, and this we get 1 of the arc cancels out, and so this turns into the square root of mg divided by r. I just derived this equation from these two equations, from the velocity which you're looking for and the period given. So I figured it'd be a simpler way to show that what the period is, and then drop that into the velocity. Alternatively, you could derive it, but this equation is not given, and so one or the other, your choice. This should be the same answer though. At the bottom of the track, there's a circular loop, radius 2 meters. Block slides on the inside of the track as it moves around the loop. Point B here is the top of the vertical track, 4 meters below the ground. What is the minimum velocity? What is the minimum value h must be in order for the block not to fall off the top of the track at point B at this point here? I don't know how good of a multiple choice question this is. This is you got a lot of parts here, bud. Alright, let's see if I can move that up a little more into the center of my screen here. Alright, so we're going around in a circle. So we have force centripetal. We have gravity pulling down. And that's it. We could in principle have a force normal. However, if we have a force normal, that means that we are too high. So that means that's 0. If we don't touch this thing here, and if we're actually going too low, then then this was not high enough. So this is actually equal to 0. There is no force normal. So the centripetal force is entirely provided by gravity at the top of this loop here. So then we have that v square on r is equal to g. So now we can solve that and find that v is equal to the square root of vr at this point here. So now we can do our energy conservation up here. So we have this here. From here to here, we have the energy conservation of mgh plus h minus 2 radii, and this is equal to 1/2 mv squared, the velocity at this point here. Another way you could do this, back up just that moment, we start out with a total energy of mgh, and then when we get to this point here on our final side, we are at mg2r, and we have kinetic energy of 1/2 mv squared. We have no initial velocity, right? And no friction. Yeah, that's good. So these are the same thing here. So then we have, so here's our velocity. Okay, good. So we back up to just that one line. Oops. And plug in, oops. What is this garbage? This is GR. There we are, right? GR, yeah, there we are. So this becomes 1/2. Oh, and the m's cancel. M goes away, M goes away. And this becomes GR. And then this G cancels with this G. Oops, and these are the same R's. So make those all capital, that makes it a little easier. There we go. So now we have 1/2 R is equal to H minus 2R is equal to 1/2 R, which means that H is equal to 5/2 R. And we're told that the radius is 2 meters, so that is 5/2 times 2 meters is equal to 5 meters. Do we have questions about that? It makes sense? Alright. Hearing no questions and seeing none. Come on. Nope. That's not clicking. That's not a clicker. There we go. Okay. Oh, a horizontal turntable with radius of 0.8 meters, so that's 4/5 of the meter, is rotating about a vertical axis at its center. A small block sits at the turntable at a distance of 0.4 meters from the axis and rotates in a circular path at a speed of 0.8 meters per second. What is the minimum coefficient of static friction between the block and the turntable that is required for the block to not slip off the turntable? This is an excellently good question for our static friction. So, oops, I'm not writing on the correct surface. There we are. So, this is a case where our static friction is the conditional force, is a singular conditional force that provides the total force necessary for our centripetal force. So this becomes mu static force normal is equal to our force centripetal, which is, let's see here, mv square on r. And force normal, let's see here, mu s mg. This m cancels with that m, and we find that, mu s is equal to v square divided by gr. We have a velocity, 0.8 meters per second. We have gravity, 9.8, and a radius of 0.4 meters. that 0.8 meters is a red herring. And I will wager that putting the 0.8 into this r will get you an answer that is also over here somewhere. And I'm going to try that because I'm pretty sure that's a thing. Going 0.8 meters per second squared divided by 9.8 meters per second radius 0.4 meters. Meters cancels meters. Right? Nope. Meter times meter is meters squared, and that cancels this meter here. This is gravity, so that's a meter squared there, and that cancels there. Oh, look at that. All the units cancel out. Very good. That's exactly what we're expecting. So 0.8 squared divided by 9.8 times 0.8. Nope, not 0.8. 0.4. And that is 0.8 squared divided by 9.8 times 0.4. 0.163. Here. Just out of curiosity. 0.8. Nope, it's not there. Huh. I would have put it there. Well. So then, of course, mu can be greater than this, and that'd be that. But this is the minimum necessary to keep this thing from sliding off. All right. Nope, not that one. There we go. Okay. Small block with a mass given at the lower end of a light rope is attached to the ceiling. Oh, did they give us a mass there? Just out of curiosity. Nope, they didn't. Yeah. If they don't give a thing, quite often that thing cancels out. And as it happened, that mass canceled out. They gave us a mass here. At the lower end of the light rope is attached to the ceiling. Alright, yep. Block moves at constant speed in a horizontal circle of this radius. Doink. Okay, very good. And the rope makes a constant angle, 36.9 degrees. It was... I don't know what that was. Looks like about 26 degrees previously. Whatever. With the vertical, how much time does it take for the block to complete one revolution? Okay. Got V. We need time to period. We need. Oh boy. Mind melting. Hold on. We have, let's see here, we have, all right, let's write down what we need. We have a V, 2 pi r on t. We're looking for this t here. We have an r, we need the v. Well, okay. A centripetal, which is what we have, is equal to v squared on r. So there's our v here, and there's that r again. So now we need to figure out what this a centripetal is. So then a centripetal, okay. A centripetal has to be the tension in the horizontal direction, and the tension in the vertical direction must be equal to mg, gravity pulling the thing up. Righto. Okay. And then, so then this angle here needs to be a relationship between that and that one. So opposite and adjacent. Yes. Opposite and adjacent. So then we have that tension opposite would be hypotenuse over tension adjacent, the vertical, is equal to the tangent of 36.9 degrees. So then you have the vertical, we need the horizontal, So then, oh, nope, this is AC there. Now the ends make sense over here. So now we can move things around. So TH is equal to TV tangent theta, a little shorter there. And then this M will cancel that M, and that's our AC. So then we need a little more space. V square on R is equal to G tan theta. And now we need the V. So then V is equal to the square root of GR tan theta. Let's compact that down into a number, 9.8, and there we are. Radius, 0.6 meters. Tan, that's a terrible 3, try again. 36.9 degrees. No answers yet. No questions yet. Square root 9. Oh, try again. Square root 9.88 times 0.6 times tangent of 36.9. And I need that to be in degrees, or not going to be the right answer. Execute. So we got velocity of 2.1. Try again. That's terrible. 2.10 meters per second. So now I can find my period being 2 pi r on v, and that is equal to 2 pi radius of 0.6 divided by AINS, 1.79 seconds. Yay! It's here. It means I probably did a good job of finding the answer. That's a little mind melting. Questions about that? No. I'm starting to wonder if Dr. Ford's writing good exams here. There's a lot of thought I put into one question there. Alright. Anyhowsen. A small rock is attached to the lower end of a light string with length of 0.8 meters. Doink, doink. The upper end of the string is attached to the ceiling. Ah, right. Here. This is our attachment point. So then it swings down here. A small rock is attached to the lower end of to the free end of a light string that has length of 0.8 meters. The upper end of the string is attached to the ceiling at this point here. The rock is released from rest with the string horizontal and swings down in a circular arc, more circular than that. As the rock swings through the lowest point, what is the string? With the string vertical, the tension in the string is 2.94 newtons. All right. What is the mass of the rock? Alrighty. Okay. Yeah, there's several thoughts going through there. All right, so we have tension pulling up, T. We have gravity pulling down, mg. And together, they have a force centripetal. So going up, tension going up, gravity pulling down. Okay. Force centripetal has a velocity in it. None of the rest of the stuff has velocity in it. We have tension. Tension goes there. Force gravity goes here. Right? Yeah. This is mg. This is okay. So we end up with mass of velocity squared divided by r is equal to tension minus mass times gravity. Yes, we do need that velocity. Okay. All right, to find the velocity, we need to conserve our energy. We have a potential energy, initial, and that is equal to a kinetic energy, final. So that's mg r, starting r up, is equal to 1/2 mv square. Masses cancel, and we end up with the velocity square of gr. I'm not going to take the square root because it's just going right there. So then we end up with m gr on r. R is canceled. That's nice. Is equal to what? Hold on. Nope. There's 1/2 here, so that goes to the other side. 2. There we go. That's better. Is equal to tension minus mg. All right. So that means that tension is equal to 3 mg. We need the mass of this thing, so the mass is equal to tension divided by 3g. Tension is 2.94 newtons divided by 3 times a 9.8 meters per second squared. Meter per second squared would cancel the newton to make a kilogram. Very good. And a nice round number. That's a sign of job well done in this particular case. If you're doing this with real work, for some strange reason, I don't know why you'd want to measure the mass of an object this way, a nice round number is probably not a thing you're going to find. Do we have any questions? Not hearing any questions. And not seeing them in chat. Moving on to the next page. A small block with mass of 0.2 kilos is projected upwards, that is sent upwards up this incline. With an angle of 30 degrees goes here, above the horizontal. Block starts with a speed of 6 meters per second at the bottom of the incline and travels a vertical distance of 1.5 meters up the ramp. 1.5 meters up the ramp of the incline before coming to rest. During the motion of the block, how much work has been done on the block by the friction force? All right. Okay. Okay. How much work has been done by the friction force? Well, let's see our work is equal to change in kinetic energy. So this is negative because it's dropping. Therefore, the work done must. Yeah, work done must be negative. So we get rid of all the positive ones. That is not particularly informative. It's here. So then this has to be equal to mgh and work of friction. Is there any other forces in here? I think that is it. Yes? Yes, that's it. So our kinetic energy, 1/2 mv squared. And see, this is what I mean by putting my friction on the final side. So I basically So our initial energy is just our kinetic energy, and then we have our potential energy. Our potential energy final, because we're at the top of this hill, is on the final side. And then here I put my work on the final side, despite the fact that it's a work other, and it should be over here. So I'm going to come up with a positive value for our work here when it should be negative. It's like the bucket is the final state of this energy is having gone into friction and making heat. That's the final state of this energy. That's why I like putting my friction on the final side, despite the fact that's on the wrong side. So let's see here. We have 1/2. Sure, let's put some numbers in here. 0.2. Initial speed of 6 squared is equal to 0.2, 9.8, there we go. And H is 1.5. So we have work of friction is everything else. All right. So that's 0.1 times, clear that out, 36. So that's 3.6 on this side, 3.6 joules here. 0.2 times 9.8 times 1.5. Oh good, this number is smaller. This is exactly what we're expecting. 2.94 joules plus our work of friction. So here's our work of gravity right here, minus 2.94 joules. I'll wager if I add these together, I'll get 6.54. 3.6 plus 2.94. Yep. And so this is what you do when this is the number you get when you do a sign error. And so you subtract this to the other side, and we find that work of friction is equal to the difference, and I'll bet you that's 0.66. Bingo. 0.66 joules. Like I said, it's positive because I put on this side. Work of friction should be on this side here, on the initial side. So if it was over here, then it'd be a negative number. So here we go. That makes sense? Questions about that? Did I actually confuse people with putting friction on the wrong, with my work of friction on the wrong side? Hearing none. A small block with mass of 0.05 kilograms in the vertical circle, okay? On the inside of a circular track has a radius of 0.8 meters, all right. When the block is at the top of its path, it has a speed of 2 meters per second. At this point, what is the magnitude and direction of the block's acceleration? All right. Well, the direction of the block's acceleration is always to the center of the circle. Since it is at the top, the center of the circle is down. Oh, look at that. Well, I'll wager I can guess what the answer is, because it's almost always never none of the above. So we have friction going down, not friction, we have gravity. So we have a force centripetal, right? Direction of block's acceleration is equal to the force of gravity plus a normal force. This is going down, that's going down. This must also therefore be going down. Oh, okay. Because we're at the top. So we can't be at 9.8. We can't be less than 9.8 because we've added normal to it. So therefore we must be at 14.8. That would be the easy way to do it. But of course, we need to make sure that is in fact not none of the above. So let's make sure that's actually the case. What is the... Oh, hold on a moment. We have a speed. We have a radius. We, in fact, don't care about any of that. We just need v square on r, right? Direction of the block's acceleration. Yes, this is the centripetal acceleration. That's all we need. That's so... I've overcomplicated things already. I mean, you can find the mass of this way, but there it is there. Why would I want to do that for? I suppose you asked the question, what's normal force? But that's not the question they're asking. Anyhow, 2 squared, divide by the radius, 0.8, and that is 4 divided by 0.8, 5. Really? That's, something's gone funny here on me. At this point, let's got velocity, block dot path, got velocity. Interesting. 5 meters per second squared. Did I screw something? Did my thinker think wrong? I bet it did. Hold on a moment. 9.8. Let me see here. 9.8. Aha. That's hilarious. Alright. Well, Dr. Ford's being kind of tricky here, ain't he? I did screw up here. Let me back. Well, this is not the answer. This is the answer right here. This is it here. Now, where did I screw up? The screw up is from the fact that you put the object on the underside of the track. He didn't specify that it was in fact the normal force holding it down, pushing downwards into the track. In fact, it's more like a roller coaster where the track is in fact holding the thing up. So if the track were not holding this thing up, this object would be falling down off of the track rather than this number here. So that's where I screwed up. I've seen this problem before. I bet I have. I remember having done this one at least once before. It was like, hey, all these things are pointing downwards. Therefore, the centrifugal force must be greater than gravity. It's not. In this particular case, the track is preventing the object from falling off of the track. So it'd be probably more appropriate to put the block on top of the track than under the track. That makes sense? That did that turn of answers make sense there? Not hearing anything. I shall continue on. This appears to be a momentum conservation question of some kind or another. Block A, mass of 4 kilos. And block B, mass of 2 kilos. Move on horizontal frictionless surface. Initially A is moving to the right at 6 meters per second, and block B is at rest. The blocks collide, and after collision, block B is moving to the right with a speed of 5 meters per second. What is the velocity and direction of block A after the collision? Alright, this is a momentum conservation question. So momentum initial must be equal to momentum final. Okay. Alrighty, so we come in, and so this is actually momentum A final plus momentum B final. There we go. Alright, so momentum initial coming in with mass and velocity, we have 4 times 6 equals some velocity to be determined times is 4 kilos. That's a terrible 4. Try again. There we go. Plus 2 times 5 meters per second. So then we have 4 times 6 is 24 minus 20 is equal to 4v. So then this is 4 divided by 4, so v is equal to 1 meter per second. I have defined that the right direction is positive, so this here is the answer I'm looking for. this would be minus 1, and these are different kinds of numbers for different kinds of for people who decide to do things funny with their algebra. Questions about momentum and momentum conservation. Hearing none.
I think the answer for that one is F on the...
Is it? Let me have a look, see. Maybe I screwed that up. That was page 3, yes. Page 3, yes. Page F. Let's see if my mind melted on something. Let's see here. This here. 4 and 2, 5, 6. Interesting, says I. Let's see here. 4. Mass is 4 there. 4 times 6. Initial velocity. Final velocity is 2 times 5. This is 4. Let me see if I can math it right. Let's see here. 4 times 6 minus 2 times 5, all divided by 4 is... there it is. I cannot math it right. Yep. 4 times 6, 24. What? 2 times 5 is 10. Aha! Thank you, Miss Flores. There we go. Right? 2 times 5 times 10. 14. Yes. So then V is equal to 14 over 4 is equal to 7 halves is equal to 3.5 meters per second. I can math it. There we go. Is it getting late yet? Alright. Hey, kindly. And 1 is there for people who decide that 2 times 5 is 20. Alright. Oh. I need draw on layer 4. Come here. Alright. A small block with mass of 0.2 kilos here is released from rest at point A, the top of a large hemispherical ball that has a radius of 1.5 meters. During the motion of the block from point A to point B at the bottom block, friction does this amount. Okay. Oh, during the travel from A to B, friction does minus 1.34 joules of work on the block. What is the kinetic energy of the block as it slides through point B? All right. Okay, that's nice. And the reason they told us this is because figuring out friction here is going to be a pain in the butt and would have to be done by calculus, and we are not calculus based, so we're not doing that. All right. So energy initial is equal to, energy initial is equal to energy final. Our initial energy is the initial potential. Our energy final is that kinetic energy that we're looking for, plus the work of friction. Note again that I put my friction on the wrong side, so this is actually not plus work of friction. This is actually minus work of friction, to make all the signs work out, right? mgh is equal to our kinetic energy 1/2 mv squared minus plus our work of friction 1.34 joules. Okay, we need velocity. Yeah, that's what asking for. Kinetic energy. What is the kinetic energy? Oh, how nice! We don't even have to figure this that much out. We just leave that as kinetic energy. So we shall. I like that idea. Kinetic energy. Alrighty. Well, I guess we're just moving that back to the other side. Oh well. M 0.2 kilograms. Gravity. We're not told otherwise, so we must be on Earth. 9.8 there are meters per second squared. H, we're coming down 1.5 meters. Minus 1.34 joules. Meter times meter is meter squared per second squared times kilogram is a joule. Or you can look at it another way. A meter per second squared times kilogram is a newton times meter is a joule. All right. 0.2 times 9.8 times 1.5 minus 1.34. 1.6 joules. That's good. It's not negative. That's a good sign. We can't have negative potential energy. We try not to do that to you guys. But we definitely cannot have negative kinetic energy. Being positive is a good sign that we did the right stuff. Come here. There we go. Ooh, springs. I'll bet there's energy involved. Yep. A vertical spring attached to the floor is compressed so that 49 joules of elastic potential energy is stored in the spring. Okay. A block of mass with a mass of 2 kilos is placed on top of the spring but is not attached to it. The spring is released and the block moves upward, leaving the spring behind. What is the speed of the block when it is 1.4 meters above its original position when it was sitting on the spring? What is the speed? Oh, fun. Okay. Alrighty. So we have a block. It's got a spring and it's going to go wee up to some height to here. So down here we initially have the given elastic energy for our energy initial for our energy initial, and then up here we have the potential of gravity plus our kinetic energy for our energy final. So mgh plus 1/2 mv squared is equal to U elastic given to be 49 joules. Alrighty. We want V. Okay. 1/2 mv squared is equal to 49 joules minus the initial our gravity potential. So that's 2 kilograms. 9.8 kilograms meters per second squared, and we got height. Where do you go? 1.4 meters. 1.4 meters. So this kinetic energy (49 2 times 9.8 times 1.4) is we have kinetic energy of 21.56 joules. Velocity V is equal to 2 kinetic energies divided by mass square rooted. So that's the square root of 21.56 joules divided by a mass of 2 kilos. Joules divided by kilos is meters squared per second squared. Under the square root is meter per second, which is a velocity. Excellent. It's the units work out. Square root, clear that. Square root of 2 anes divided by 2. So that's just square root of 2, square root of the anes. 2 cancels 2, so that's square root of anes, and then that comes out to be 4.0 4.64 meters per second. 4.64 meters per second. A block with a mass m is attached to one end of an uncompressed horizontal spring. Okay. Mass is attached to a horizontal spring. Force constant K. A force F is applied to the block and compresses the spring a distance of this much. How much work does the force exerted by the spring do on the block while the spring is being compressed? Okay. All right. So we have that we have a spring being compressed by a block. So we have a force F goes this way and S goes that way. So that means the work is equal to F dot S. As these are in opposite directions to each other, this becomes minus Fs. It's technically an integral here, but we don't need to do that integral because this work is equal to the potential, which, because it's positive, must be negative. So then the work done by that spring on the block is minus 1/2 kx squared. Does that make sense? I just need to I did this here to make sure I got the sign right, but I knew that the work done on the block by the spring must be equal to its potential energy. This is also equal to the energy stored in the block, stored in the spring, and has been placed there by the force F. So then we have minus 1/2. K is 40 newtons per meter, and the displacement is 0.150 meters. Quantity squared. This meter squared, this becomes meter squared, cancels 1 meter here, which leaves me with a Newton meter. Newton meter is a joule, unless it's torque, in which case we leave it as a Newton meter. So that is 20 times 0.15 squared is negative 0.45 joules. Let's make sure I didn't say something stupid, because we're always so close to saying stupid things sometimes. Negative 0.45, very good. Sometimes because of how prepositions are worded, it's like, what? Why did you ask that question? Why not ask the question, how much work was done on the spring? That'd be a much more simple kind of question. That was the last one, right? Let's see here. Nope, not that one. This one. Yeah. All right, page 5. Block A, we have a mass of this much. Block B, a mass of that much. Horizontal frictional surface, a light spring is compressed between them, but isn't attached to either block. The two blocks are released and moving off in opposite directions. After leaving the spring, block A has kinetic energy this much. What is the kinetic energy of block B after it leaves the spring? Okay. We have velocity there. We know precisely nothing about the spring. Okay. That's fine. This is I'm not writing on the right layer there. There we go. Now we're writing on the right layer. Okie dokie. This is a momentum conservation question. In principle, we could ask this a question about energy in this question. Well, and we are, but it's not. We could do it by energy conservation, but they didn't tell us anything about the spring. So we know precisely nothing about the spring, but we know everything about the momentum of these two blocks. Initially, let's start off with P initial is equal to 0 is equal to P A final plus momentum of B final, which means that momentum A final is equal to momentum B final. All right. Okay. Okay, let's see here. We're told this, we have kinetic energy this much here. We can't assume that it's that much in the other one, but we do know that momentum has been conserved. This here. Kinetic energy I'm going to do a thing because I suspect that this equation is going to be handy in this one, is equal to 1/2 mv squared. Momentum here is mv. So if we let's here, multiply that by m and divide by m. So let's here, we square that and divide by m. We now have p squared divided by 2m. So we have a kinetic energy. There it is there. Oops, that'd be equal and opposite. Let's see here. So now we have that 2m kinetic energy is equal to momentum squared. Oh, we don't want to square. We want the square root of that. Oh, look at that. Momentum A, which is equal to the same thing as momentum B. That's really stinking handy. How about that, Humdinger? I'm so glad I did that. 2 mass. So let's see here. That's 6 kilos. Times its kinetic energy, 24 joules. Is equal to, our answer is equal to, oh, right? Yes. And then, actually, let's not do that. So then, so that's for A. A goes there. Let's just back up just a bit more. So 2mk is equal to momentum A squared is equal to momentum B squared. That's the kinetic energy of B after it leaves the spring, right? Yes, good. So now, oh, let's see here. Kinetic energy, so let's here, put an A here and an A here. So now we need kinetic energy B is equal to P squared divided by 2mb. Get my 2, that's a mass of B, mass of A, kinetic energy of A. That goes away, that goes away. So we end up with mass of A divided by mass of B times the kinetic energy of A. There we go. Let's plug and play on that. That's a nice friendly equation there. That's probably way too much work. And way too much thought. Anyways, 6 Okay, so that's 6 divided by 2 is 3 times 24. 3 times 24 is 72. That's a lot of work to keep things all simple like this. You might just be faster off by determining the velocity on A, plugging it into here, determining the velocity of B, and then putting it back into here to find the kinetic energy of B, because you have all the equations for that. But this should work out to be the same. Should I double check my handiwork by going through that the long way? Or should I just go ahead and leave it with this lovely equation right here? Ms. Flores, should I proceed on, or do you need to go through the 4 steps to get to the answer leave it? Very well. I shall leave it and move on. All right. Alright, block with mass of this much slides a distance of this much, 3 meters, from A to B up a ramp that is inclined 30 degrees above the horizontal. How much work does gravity do on the block as it moves from A to B? Okay. Well, and must do 2 steps here. Okay. So we actually need H, which is opposite, and that's our hypotenuse. So opposite over hypotenuse, that would be a sine theta. Therefore, H is equal to 3 meters sine 30 degrees. I'll wager that's a half. Come here. Sine of 30 is, yep, that's a half. 1.5 meters. So basically, we're going to answer another question, part of a different question. There you go. Basically, finding out how much work was done in this problem here. Right, 2 kilos, maybe. Nope, different mass. Similar question, different mass though. So much work was done. Work is equal to minus potential in this particular case, equal minus mgh equals minus 0.4 kilos. Gravity is 9.8 meters per second squared. H is 1.5 meters, 1.5 meters. 0.4 times 9.8 times 1.5. .88 joules. Work was done because it slows down, so this should be negative. Don't drop the minus sign. All right. That was the easy way to do this. That's probably not what they're expecting. What they're probably expecting us to do, they're probably actually expecting us to do work is equal to force displacement cosine theta. All right. Okay. Let's see here. So we have that force. We have, so on our block we have force pulling down. Yeah. And we're going to use so this is not theta here because it's the angle between the force and the direction traveled. So it's actually this one here. So it's actually phi. So it's not that one, it's this one. So then we end up with force, we have our mg pulling down, the distance we travel, d, cosine 60 degrees. So we end up with, where'd it go? 0.4 kilograms, 9.8 meters per second squared, cosine of 60 degrees. Oh, and our distance traveled. Distance traveled is 3 meters. Should come out to be the same. 0.4 times 9.8 times 3 times cosine 60 degrees. 5.88. Yep. 5.88 joules. And again, we're going up while gravity is pointing down. So then these must be pointing with a minus sign, minus sign, minus sign, minus sign. So this is exactly the same thing as minus mgh. All right. A block is moving. How many more of these? Oh, one more page beyond this. Yay, almost done. A block is moving on a horizontal surface at point A. Horizontal surface, okay? At point A, the block has kinetic energy of 60 joules. During motion of the block to point B, the forces on the block do total work of minus 20 joules. What is the kinetic energy of the block when it reaches point B? All right. So we are at point A, and it moves to point B. We have 60 joules here. Work done is equal to minus, nope, not that. My thinker's thinking too fast. Minus 20 joules. How much energy do we have right here? Oh, that must be our kinetic energy initial minus the work done. But not that minus, because so I need to rearrange this just a little bit. So work is equal to change in kinetic energy. That is kinetic energy final minus kinetic energy initial. So then we move that to the other side. So we have kinetic energy initial plus the work done is equal to kinetic energy final. I can fill that in. 60 joules there minus 20 joules there means that this is equal to 40 joules. And the 80 joules is there for people who can't keep their signs straight. All right. A small rock with a mass of 1/10 of a kilo is projected straight upwards from the ground. Check straight up. Okay. When the rock is 5 meters above the ground, it has a speed of 8 meters per second. What is the maximum height above the ground reached by the rock? Okay. All right. So, mgh is equal to 1/2 mv squared. We're going to go ahead and not consider the ground to be 0. We're going to consider the 5 meters above the ground to be our 0. Keep things maybe simpler. There's a chance of forgetting things though. There's a chance to do that. And so we're going to turn all of our kinetic energy that we presently have and turn it into energy over here. What you could do to make sure you don't screw anything up is go 1/2, put our mgh of 5 meters here. Right? Yeah. And then find our maximum height over here. Do we want to do that? Yeah, we want to do this. Let's not screw things up. So our initial state, 5 meters above the ground, goes here. With that kinetic energy for 8 meters per second. We want to know final height. We don't care about that m, it cancels out. And we'll go ahead and divide g to the other side. So we find that h is equal to v squared on 2g plus the h initial, just like I was going to before. So then that's 64 meters squared per second squared divided by 2 times 9.8 meters per second squared plus 5 meters. This cancels with all of that, leaving us with 64 divided by 2 times 9.8 plus 5. 64 divided by begin, 2 times 9.8, end plus 5. .27 meters. Rounds to 8.3 meters. Let me guess. If the plus 5 is not there, we end up with 3.26. Is that there? Ah, it's not there. Okay. That would have been an excellent opportunity to see if anybody else misses the add-up. But no. And you don't. And that's alright. On a horizontal frictionless surface, block A, mass of 4 kilos, is moving east with a speed of this much, and block B is moving north with a speed of that much. The blocks collide and stick together. What is the speed of the combined object? Mass of 12 kilos, 4 plus 8, yep, that's 12 kilos, immediately after the collision. Oh boy, lovely. Okay. Okay, yep, we can do this. Oop, let me drawing on that layer. So we have in the east-west, we come in initial with initial momentum, initial, velocity initial, and then becomes is equal to momentum final. So a mass initial, velocity initial, is equal to mass final, velocity final. Initially, in the east-west direction, we have 4 kilos. And 4 kilos and 8 meters per second. So we end up with V final is equal to mass initial, V initial, divided by mass final in the east-west direction. That is 4 times 9 divided by 12. And that does divide evenly. So that's 4 times 3 is the 12 divided by 12, and leaves us with 3 meters per second in the east-west direction. In the north-south direction, same equation, V final is equal to our mass initial, 8 kilos, times 6 meters per second, divided by 12. Take a 2 out of the 8, and so that's 12 there. 8 divided by 2 is 4. 4 meters per second. Oh, that's nice. We're going one direction and the other direction. 4, 3. So that means that this is 5. Questions about that? That momentum makes sense? A small car collides head-on with a large truck. Which of the following statements is correct? Small car runs head into a large truck. Small car undergoes a greater magnitude of momentum than the truck. The truck undergoes a greater magnitude of momentum change than the car. Both cars undergo the same magnitude of momentum change. Oh, yes. Okay. This here, P1, 2, nope. PI1 plus PI2 is equal to PF1 plus PF2. Rearrange this. We get PF1 1 minus PI1 equal, so basically put that there, which means I had to move that to the other side minus that. So then this should be, let's see here, I went way too far on that one, too fast. Let's put 2 on the left side. So then we put P, nope, sure, minus PF2, which gives me PF1 minus PI1. So this is minus P delta P2 is equal to delta P1. Oh, look at that. They're the same. The magnitude is the same. They're equal and opposite to each other. A bullet with the a bullet with the I could explain what's going on there. There's some Newton's second, some Newton's equal and opposite forces are being applied there, and momentum conservation and stuff like that. But that's getting into some RDR proofs that we are not equipped for at 9:43 in the evening. And y'all don't like proofs anyways. A bullet with mass of 0.05 kilos is traveling in a horizontal velocity of with 200 meters per second. Just before it strikes a wooden block that has mass of 1.95 kilos that is initially at rest. What is the speed of the block just after the bullet has become embedded in it? Alright. Momentum initial. Momentum final. Mass initial. Velocity initial is equal to mass final. Velocity final. Therefore, velocity final is equal to mass initial and velocity initial divided by mass final. Alright, mass initial is 0.05 kilos with a velocity of 200 meters per second divided by 0.05 plus 1.095 is 2 kilos. 50 grams. That might be a bit much for a bullet. I don't know. Anyways, maybe it is. Maybe it is, maybe it isn't. So this is to do kilos, yep, yep. Let's see here. So kilos cancels there. 2 cancels with the 100. 100 times 0.05 is 5 meters per second, right? I think so. Let's make sure that's what it works out to. Yep. Make sure to do that right. Very good. I did. Questions? Interesting. A 6 kilogram block of ice is sliding along 18 meters per second on the floor. Of an ice-covered valley when it collides with and sticks to another 6 kilo block of ice that is initially at rest. The combined object then slides up a hill. There is no friction with the blocks in the valley and the hillside surface, which is complete bunk, but whatever, and maximum vertical distance above the valley floor due to the combined. How far up do they go? Alright. Okay. We're going to recycle this equation right here. So our velocity final is equal to 6 kilos there, another 6 kilos there, okay? So we go 6 times 18 divided by 12, 18 is 9 meters per second. Now we go for this one here. We have, this is an excellent opportunity to show why there's another, so there is an equation in the kinematics called, where it goes v squared is equal to v naught squared plus 2ad. And I like to call this the energy equation. And this is the opportunity to show why I like to call it the energy equation. Energy initial is 1/2 mv squared. And that is equal to our kinetic energy final, 1/2 mv final square, right? No, put our initial there, plus 2a plus 2 mgh. M's cancel out. Oops, that 2 does not exist there. Just mgh. The m's cancel out. Multiply everything by 2, and we get v squared is equal to v naught squared plus 2gh, which is more or less what this thing here is. Just that there's things are hiding. Anyhow, we have a velocity that's equal to our kinetic energy, and this is equal to 0. So then we end up with v, right? Oops, no. We need the height. So we get v squared on 2g is equal to the h. V v, right, 9. 9 squared is 81. Divide by 2 times 9.8. And that is, clear, 81 divided by 2 times 9.8. 4.13 meters. All right. Okay, and that is the end of that exam. Are there any other questions that I can answer? Yes, here, Ms. Flores has still here. Any other exams? Any other questions? Any other hypotheticals that may involve these concepts? All right.
This could just be a really ignorant question, but sometimes whenever you're talking about centripetal acceleration, you just do b squared over r, and other times it's mv squared over r. How do I decide when that's included?
So the question is more of the question when I decide what to do one or the other is when I think I need the centripetal acceleration or when I need the centripetal force, and sometimes I skip past dividing out the m's. So let's see here. Is there a particular question? Let's see here. Sometime.
On number 8, you just used. I'm just looking at some work that I wrote down. You just have v squared over r, and then in other instances it was the mv squared over r, and I just didn't know when to use which one.
Right. So let's see here. Number 8 here. So I was on number 8 here. It's just wanted the acceleration, and so I stopped by. I didn't have to do any of this other stuff here. If I needed to, if this question had asked, so this question asks, what is the direction of the block's acceleration? And so I know that the acceleration is just the centripetal acceleration, v squared on r. If the question had instead been, what is the normal force applied to this? Oops, let me pull up, let me see here. If it instead asked for the normal force, then I would have to go mv squared on r, and then minus the mg, and then normal would be this, and then I could find out what that is. This here, do they provide mass? They do. So then that'd be 5 minus 0.05 times 9.8. Right. Right. Mass there. 5. 5 is the acceleration. Right. So that's the v. So that's the v square, vr square here. So I need to multiply that by mass there. 0.05 squared. And then I would find that the normal force is equal to minus 0.25 4 newtons. And so the only way I would know what the newtons is, what the normal force is if I actually found what the centripetal force was. So this is the net force required to go in this circle here with a velocity of 2 meters per second. But in order to find the normal force, then I would need to actually get the centripetal force, rather than just looking at the centripetal acceleration. Is there another question where I might have been different on that? Let's see here. A.
That makes sense. And then another instance like that, but not that particular equation, is whenever in the worksheet or this with all of the equations, it's just negative kx for the spring.
Yeah, negative kx.
But we use 1/2 kx squared. Why do we use?
So that's the difference between force of the spring itself versus the that's the force provided by the spring versus the energy stored in the spring, or sometimes energy stored applied to the spring or whatever. So this is the energy stored in the spring, and this is the force provided by that spring. So the question then becomes: is the question, in order to get to the answer, do you need the force of the spring or do you need the energy of the spring? Most of the time, it's going to be the energy of the spring. But there are a few cases where, let's see here. Let's see if I can find. What do you remember the problem that had the spring constant in it?
I'm looking at number 12 at the moment.
Number 12. Yeah, the spring. Here's our spring constant here. So then, in this particular case, a force F was applied. So this one here wanted to know how much work was being done to the spring, and so in this case, I had to use the 1/2 kx squared because that's the work that's being used to store energy in the spring. But if the question had instead asked the question, if it had instead been, how far? Let's see, force. Let's see here. I got a spring constant here. I have the energy stored in it. We have the distance. So if the question was instead, how much force does the spring give, or the force applied to the block by the spring, then we would have to go F is equal to minus kx, and then we get the minus, and then the k is 40 Newton per meter, and then that's the minus 0.5150 meters. Meters cancels meters. That leaves us with the force of 60 joules. 60 newtons minus 6 newtons. So 6 newtons in the direction opposite of its compression, wherever that direction might be.
Okay, thank you.
All right. Any other questions? I believe I have one viewer there. Having no further questions from either my Zoom chat or from my Twitch chat, I will go ahead and conclude the stream at this time.